Hi everybody. I'd like to show you how we're going to use visual techniques to navigate autonomously on Mars. First, I'm going to begin by motivating my work by telling you why we're using visual techniques. Then I'm going to give you my proposal for the solution to the problems that motivate us. I'm going to give you some basic theoretical background so that you can understand my solution. I'm going to show you how I brought my solution to life, the results, and future work. We begin with the mission of the Autonomy Incubator, which is to deliver packages, whether these packages be physical or data or whatever. And we also have a related mission, which is NASA Langley's internal Mars Flyer effort to explore Mars in 2020 or 2025. And I argue that for both of these autonomous missions, vehicle localization, meaning the question of where am I, where is the robot, is essential. This is a question that the robotics community has been working on for about 30 years. And only now are we getting to the point where we can answer this question reliably. This is a difficult question because we operate in environments that are both unknown and unstructured. This is clearly true on Mars, but people think it's not true on Earth, even though it actually is. Google Maps tells you where you are within the national road system, but it doesn't tell you where you are relative to this television, to this computer, to that person. The features in our environment of interest are on the meter scale, which means that in order to safely operate, we would need sub-meter precision in our localization. And we arrive at the major problem with localization, which is that the tools we have available are simply not good enough. These tools, the two most popular, global positioning systems and motion capture systems, are both insufficient. GPS can only give us 1 to 3 meter precision. It fits on our vehicles very well because of its low cost, low weight, but it doesn't work in interesting situations such as indoors, beneath a tree canopy, and on other planets. The state-of-the-art in localization is this motion capture system used in the film industry. It has millimeter precision, meaning it can tell you where your object of interest is within millimeters. And it gives you this information 200 times every second, but at the cost of total impracticality anywhere outside of a laboratory. This is why I propose that we use visual techniques. I propose visual techniques, one, because they give us exactly what we want, which is the pose of the robot, in exchange for low weight, low cost, and only the cost of sending the information from the camera to the computer. I also propose the solution because NASA has a history of using visual techniques. In the Spirit and Opportunity missions, we used primitive 1990s forms of visual odometry to guide those rovers on Mars. Today we're going to take this to the state of the art. Now I'm going to begin by telling you some theory that is going to help you understand the solution, the visual solution. And this slide shows you how computers interpret their environments. As a human being, I can stand here and I can observe this rock. And then I can walk over, and by re-observing the rock, I can see how far I've moved away. In a computer system, we extract features from our environment using a mathematical technique called FAST. We take in an image, we grayscale it, and given a candidate feature, which in this case is this pixel P, we study the pixels around P, read the intensity of light that they've measured, and if we find a contiguous arc, such as this dotted arc, in which every pixel is brighter than P or darker than P, we identify this as a visual feature. These features tend to be high contrast corners, such as the corner of this television or anything else you might imagine. Then, once we find features such as this, we move the camera naturally, right? Just like how I moved on Mars, we can move our camera. And because the description, the numerical description of the features is unique, I can identify a feature at one camera pose, I can move the camera, and then I can re-identify the same feature. This procedure is called feature matching. By finding a feature in one camera frame, moving the camera, re-identifying the same feature, noticing the motion of the feature in the camera frame, we can then triangulate, we can back calculate the motion of the camera itself. This procedure, this 4-step procedure, is the essence of what everybody is doing in computer vision. This is the essence of motion estimation from a camera. Here I demonstrate for you the effectiveness of this method. Here you see 2 images which are subsequent video frames. And you can even see a subtle change in the position of the camera, represented as the change in the way the house appears in the scene. These crosses here are visual features extracted using the FAST technique. And these parallel lines represent the re-identification of the same visual features in the next frame. So this shows you that what I just described is effective on Earth. But now we must ask ourselves, is this effective on Mars? And the answer is emphatically yes. This is a photograph taken from the 1997 Pathfinder mission. And here I performed a feature extraction on the same photograph. You can see how rich this barren wasteland appears to a computer. Now that I've told you the fundamentals of how we do visual-based motion estimation, I'm going to, in one slide, summarize for you the absolute state-of-the-art in what we call visual odometry. This is called semi-direct monocular visual odometry, meaning monocular meaning from just one camera. And this was invented at the University of Zurich. I'm going to divide this entire work into just 2 steps. The first step is where we attempt to make an initial estimate of the camera pose. Assume that this rectangle is the first image frame, meaning as soon as you turn the camera on, and then assume that this rectangle is the second image frame. We assume an initial pose. So as you can see here, the vehicle has a known initial pose that we can use as an easy assumption. And then we assume a transformation between the initial pose in frame 1 and the pose in frame 2, meaning we just guess at what the camera motion was. Next, based on our assumed transformation, we project the second view onto the first view and subtract them. This gives us an error. So now we have an assumed transformation and an associated error. With this information, we modify the assumption and observe the change in the error. If the change in the error, if the error decreases, then we modify the assumption again. If the error decreases again, we modify the assumption again. And we repeat this sort of gradient descent procedure until we reach a local minimum. And at that point, we say, that was a good assumption. This was done in 2 frames. As you can imagine, you do this between frames 1 and 2, frames 3 and 4, frames 5 and 6, and you do this at the camera frame rate. One issue appears, and that is, if you made errors in your assumption, the cumulative effect of these errors increases over time. This is what scientists call drift. Like the people who do controls, they call this drift. And now, at this moment, is when this expensive, complex feature extraction technique comes in. We perform feature extraction occasionally, and then we save the feature extraction points. We reobserve the features, and then we use the feature information inside of this transformation optimization technique to reduce the error. So at a high level, this is the state of the art in odometry. Excuse me. One other thing I wanted to mention, the importance. It's called semi-direct visual odometry. Direct meaning operate directly on the raw image intensities. Indirect meaning operate on extracted features. Here we do both. This process operates on the raw image intensities. This process operates on the features. It's this feature extraction that's expensive, and it's important to understand that we're able to reduce our computation by only performing the expensive step occasionally and using it only as a correction measure. Now I'm going to tell you how I implemented the state-of-the-art method on our Mars Flyer hardware that you can see here and over there. My idea was to take the software, to make it work on a vehicle by enhancing it for what the vehicle needs, and to then test this procedure against the pose estimates that are provided by our motion capture system. This will give us a way to validate if this state-of-the-art method is useful or not. The hardware implementation, you've heard, it's a Mars Flyer. It has an 8-core ARM computer on board. It has a 70 frames per second camera. It has Wi-Fi, and it looks down at the simulated Mars surface that we're going to use for feature extraction. The software, we use a full Linux operating system on board. We use the robot operating system for communications, plumbing, and for live visualization. We used a modified public implementation of visual odometry, enhanced for robustness, that can automatically detect tracking failures and then reinitialize itself in real time. And then we interface with the DDS internal software framework that Gil mentioned in order to make this work applicable to any project inside this building. This is a flowchart of that shows you the breadth of the integration effort that the Autonomy Incubator had to do to complete this work. You can see all of the moving parts. And the important message that I want you to get from this slide is the flow of the information. You notice that we use the Linux desktop here for visualization and validation. You notice that the Vicon motion capture system sends information here. But you also notice that there's no help from Vicon, from GPS, or any other crutch information source. We use only the camera as an information source. We do all the visual odometry computation on board the vehicle, and then there's only one arrow showing information flow from the vehicle to the computer. It's just the vehicle saying, I'm here. So no help from external computers, no help from crutches like motion capture. And now I'm going to show you the results of this experiment, the results of doing visual odometry versus Vicon. Here we execute the experiment that I just described to you in the last slide. I'm going to play this video for you now. On the right side, you see a live visualization of the vehicle position. You can see how immediately the visualization shows exactly how the vehicle moved. And you can see that even small sways in the motion of the vehicle are picked up by the odometry. And furthermore, down here, you can see the picture of our simulated Mars surface with the feature extraction points shown for you. And another element is that here in the visualization, it might be slightly hard to see, we also map these features. We map them in 3 dimensions relative to the position of the vehicle. And I'm just going to enjoy this for a minute. You notice our pilot Zach. He's doing some sinusoidal maneuvers, some curves, 90-degree turns, whatever you want. And we're even capable of recovering. If you ever see a big gap in the data, such as maybe right there, we're able to automatically recover from random failures. This algorithm is not deterministic, it's stochastic, and so it has failure modes that sometimes just happen. And we're able to automatically recover from that. Okay, I think that's enough for the video. We haven't yet done the apples-to-apples comparison. We've seen this beautiful visualization, we've seen how live and fast it is, but we haven't compared numerically against the position data from Vicon versus the position data from visual odometry. And now we do exactly that. In blue, we have the XY location determined by the motion capture system. In red, we have the XY location determined by the visual odometry. If you read the scale on the graph, you'll notice that at most we're off by centimeters. We've achieved centimeter accuracy with only a camera. And another element of this is I specifically picked this data set to show because it shows this big red gap in visual odometry, which is an automatically recovered tracking failure. Here you can see the data in 3 dimensions, and you can see that our accuracy in the Z direction is just as good as our accuracy in the XY direction. This slide is the same data here, simply viewed from a different angle. What's a summary of our results? We get centimeter accuracy 70 times per second at the camera frame rate, meaning we're limited by the camera, not limited by the computation aboard the vehicle. This implies that you can run, in addition to my work, you can run your own algorithms with computing power to spare. SVO needs only 2 cores of 8 on the Odroid. And furthermore, we beat the kings of localization. We've beaten GPS. We're way more accurate than GPS by a factor of 10. We're way faster than GPS. And then we've beaten the motion capture system by a factor of infinity, right? It's totally impractical, and we're totally practical. This is immediately useful on Earth and Mars. And again, I want to emphasize, because the software is light and the hardware is light, you can put this on any vehicle you want. I mean, just look at it. What's the work remaining for the future? You've heard a previous presenter, Josh, talk about sensor integration, sensor fusion. We're only using information from a camera. We would be even smarter if we fuse this camera information with some inertial information from an inertial measurement unit in order to get an even better estimate. That's a clear next step. Then a further development would be to integrate Javier and Bilal's autonomous trajectory following work, but without the motion capture system. And even more work we could do is we could do 3D reconstruction. We could fly through a scene. We could, knowing our position from odometry, we could map points of interest in 3 dimensions and reconstruct a 3D scene in a human-readable way. Those are action items for me, but the action items for you in the audience, people in the incubator, anyone at NASA who has a vehicle, use my work. The code is on the server. The computer and the camera cost less than $600, and I wrote a documentation that has step-by-step instructions for how to use this. I'd like to thank Loctran, Jim Nealon, Danette, and Danette for their leadership, for teaching me, and for mentoring me. Zach Johns for being an amazing pilot. Dave North for heading up the Mars Flyer project and for giving me the opportunity to apply my work to a Mars mission. Gil Montague for helping me with code. Carol Castle and Bill Kluge for making this Mars surface possible, this essential element of my work possible. And also the first author of the semi-direct visual odometry paper. He and I have been in contact, and he pointed me in the right direction for this project. And now I'd like to take questions.
Great. Shall we move to the live demo?
Sure.
All right. So we're going to have to close the net.
Yeah, I'll get it.
And then we're going to turn this around so Alex can actually see what's happening.
All right, ready to go, Zach. how Zach can do pretty fast, pretty abrupt maneuvers, and the camera will continue to track what you saw right there. You move a little too abruptly, you were able to recover from the loss of the Anyone have any other questions? Personally, I think higher speed is navigated only positive. That's it. Landed. If y'all have any other questions, if not, we're done.
Terrific, thank you, Alex.